So, hello everyone. Thanks again for joining us today. Today is day 14 of the RH Online course, and I think it's going to be the last one. So I hope you have enjoyed the course and you will enjoy today's class as well. So today we will learn how to run RH in parallel using the Python wrap or the method described in Ricardo's paper last year, so this year, sorry. And we are going to cover this method in 2 steps. So the first one is that we are going to relearn or learn again how to adapt the Bifrost atmosphere to be used in the parallel wrap. It's not so different, so we are going to use the same script that we use in day 8 of the course, but we are going to change some minor things at the end. Okay, so after that, when we have the input atmosphere, we will learn how to run the code in parallel. And in particular, we are going to repeat the same computation that we did in day 9, and just to check that the results are the same, and then we can compare also the time we need to perform the computation. So today I don't have any special thing related to the class, so then we just stop here the presentation and then we can go to the scripts. So as always, I will put things on the Dropbox folder on day 14. And as I said, we are going to have 2 parts. So the first part will be a folder that I put it in my RHF1D just for simplicity. And it's called Bifrost Transform Parallel. And there we are going to cover this script. Okay, just let me move it a bit inside so I can see it properly. And then you can also see what things we have here. So as I said, it's basically the main script or the same script that we use in day 8. So we are going to cover it relatively quickly and stopping only just on some things just to be sure that we are understanding what we are doing. And then we will go slowly on the new things that we need to add. So what we are going to do is first, as we did, we download the Bifrost simulation and we're going to load it. Just for simplicity and for avoiding you to go to the day 8 folder and read the atmosphere from there or copy it, I just put everything that you need in the same folder. So then when you download this file from the Dropbox folder, everything is here. So inside this folder, you have the original atmospheric parameters from Bifrost. Okay, so you don't need to download them and they will be here. So then we just specified that this snapshot 385, that is the one that we usually use in the literature, has been mostly used in the last year. We just indicate where they are, and then we start reading all the parameters. So we start with the temperature, and if you remember, it was saved as a log scale 10. So then we just need to revert that and to put it in the natural scale. Then we read the geometrical height. In this case, if you remember, we said that all the atmospheric parameters, they contain the information of the geometrical height and is encoded in this instruction, in this extension instruction. And if you put extension -1, then you can read it in any parameter. In this case, as we already use the temperature here, I just copy it and then added this, okay? And for RH, we need it in kilometers, so we are already multiplying this by 1000. And then we're going to continue reading the atmospheric parameter. Line of sight velocity. You remember in day 8, we made a plot just to check the sign, and we confirmed that the sign that the Bifrost atmosphere uses is the same that we need for RH. That is the opposite of Sarah on this side, so we don't need to change anything. Just read the feeds file, and then we have the velocity that we need. Then we have the 3 components of the magnetic field vector in Cartesian coordinates, so Bx, By, and Bz. Then electron density, that is also in log scale, so we need to put it back to the natural scale, that is the one RH will use. And then the 3 the 6 hydrogen level population that are in non-LT in this run. And all of them are also in log scale, so we just repeat the same step that we did before. Okay, so until this point, we are just reading the feeds file from Bifrost and just making minor changes that we need to do for providing the atmosphere to RH. Then the next step that we did in day 8 was that the simulation goes from very deep in the atmosphere up to the corona. And we said that for most of the lines that we are going we are interested on, like the calcium infrared transition, we don't need to go up to the corona. We can cut it lower. We can save time, and maybe we can also avoid some problems that could appear if the atmosphere is not very stable or is complex in upper layers. So then we said that probably it's safe to just go from almost minus 1000 to 3500. But remember that we discussed that maybe you want to go a bit higher just to be in the safe side, or if you want to include the calcium H and K lines, and if you want to be certain that you are not cutting the hydro formation of the lines, you may go a bit high. But I think for calcium 8542 is probably enough. So we just define the upper and lower limits, and then we define the diameter of points that we will have in the spatial domain. That is 504. That is the total domain of the simulation. And then here is a very simple instruction. That is, we are just using the full horizontal domain, X and Y, and we are just cutting the vertical domain from the lower to the upper limit that we defined above. Okay, so with that, we are reducing the size of our cube, and we can go ahead. And then the next thing we did was the magnetic field that RH needs is in spherical coordinates. So we need to transform the original one from the simulation in Cartesian to a spherical coordinates. And for that, we are going to run a loop that goes on X and Y. And for each pixel, we are going to compute the field strength with this instruction, the inclination with this instruction, and the azimuth with this instruction. Okay. And with that, we have also the magnetic field vector in the format that we need for RH. And the last step is that the Bifrost atmosphere, the first index in height, it corresponds to the lower part, to the lowest part of the atmosphere. And RH needs that behavior in the opposite way. So the first index should be the top of the atmosphere, top boundary, and then the last index of the vector should be the lower part of the atmosphere. So for that, we are going to reverse in a loop all the atmospheric parameters. Okay, but also we are going to use the same loop for creating the array that we need for the Python wrap, for the parallel wrap. So for that, here I'm highlighting. You will see that there are several parts on the script where I highlight this. So we are going to use these conversion factors later on. So I'm writing them here outside the loop. And also we are going to save all the atmospheric parameters in this file and this array. I call it test, but you can call it other name. And it's going to be, the dimension will be X and Y. Remember that this is 504, 504, then 14, and then the number of geometrical height points. And 14 are the atmospheric parameters. This is similar to what we see in what we saw with SER. In that case, we're 11. And in this case, the 14 parameters are the thermal part, so the scale, the height scale, but in this case, it's geometrical height. Then temperature, electron density, velocity, and microturbulence. So this is 5. Then you have the 3 components of the magnetic field, field strength, inclination, and azimuth. This is 8. And then you have the 6 hydrogen population levels from N1 to N5 and then NP. Okay, and this is the total 14. So this text, this script, this is for the previous case, so what we did in date 8, and this is how we create the file for the Python wrap. I kept both things just to allow you to compare, but the idea is that for today we only need this part. Okay, so then what we are going to do is we are running the loop. Remember that is for x and y are the first two dimensions. Then we fix this because it's the the atmospheric parameter. And then this asterisk is all the geometrical height scale values. Okay, so then 0 will be geometrical height, it is always the same. But for example, 1 will be reverting the original atmosphere temperature, and it will be for these peaks. Okay, so we are also using the loop for reversing the atmosphere, but I'm adding factors in some of the atmospheric parameters that they were defined outside the loop. And I'm adding these factors because I don't know if I explained it properly when we covered class day 8, but write 1D at most, the ideal procedure that we use internally, it transforms the atmosphere that we give as an input and write it down to the Atmos file with a different unit. So internally it was doing a conversion. So what we are doing now is the same conversion that was done inside the ideal procedure, but we are doing it now because in the case of the parallel wrap, this is the atmosphere that we are going to pass the code. So we need to have the atmosphere with the same units as it should appear in the Atmos. For example, here if you see my mouse, as they should appear in the Atmos file. Okay, so then we just run the loop, and just one thing, I put the labels, I think they are correct. So I'm almost certain that what is inside is correct. What I'm not so sure is about the labels. So if you have time, please try to double check them. So try to check what are the units of the bifrost atmosphere and what are the remaining units when we apply this, because now I'm not so sure, but the values inside, I think they are correct. We will do a lot of double checks, but what I don't trust too much is this. So maybe it's a good homework to just double check if this is correct or not. Okay, so then we just run the loop and we are saving all the atmospheric parameters in this test array with the proper format and also reversing the axis and everything. So I commented this line because this is from the day 8. And what we are going to do now is a similar thing, but it's just using the right fits function from IDL. That probably if you use Python, there's going to be something similar. And we just save the test file with this format. Okay. So until this point, because now is where the things get interesting. So until this point, we just did essentially what we covered in day 8 with minor tweaks related to the Python wrap. But the things are the same. Reading that the bifrost atmosphere and put it in the proper format with the proper units. Okay. So then, as I said, it's a bit difficult sometimes to track that all the conversions are done correctly. So I always try to, before even running the code and check that everything is not consistent, I just try to double check that what I'm assuming in terms of conversion and other things is correct. So what I did is I went to day 9 to the example that we have in day 9. I ran the loop for all the pixels, just one. And then I save the atmosphere, the thermal part and the magnetic part. And this is for the pixel 60 and 150 of the full array. Remember that we cut it in a small piece. So the initial X position of this piece is 60 and the initial Y position is 150. So I saved that atmosphere and it's the one that you have here. So this is the thermal part and this is the magnetic part, okay? So then what I'm going to do now is print the values on test, that is our array, for the pixel x60, y150, and then the initial height. So it should be the initial value that we have in our Atmos file, and then for all the parameters, geometrical height, temperature, electron, velocity, and this thing, okay? And the magnetic field is not included here because we will do it later, but just check the index. So 0, 1, 2, 3, 4, and then we jump to 8 because the magnetic field is 5, 6, and 7. So field strength, inclination, and azimuth. Okay, so then this is what you will see when you run the code, and I'm going to open this file. So then just let me make this a bit bigger, and then I will do this, and then we go back to here. Okay, so then as I said, we are printing for the array that we have created, test, the information of the first value for 60 and 100, for the pixel 60 and 150. So then what you are seeing here should be the same as the one that you see here. Okay, so then you can see that they match, except some not the same accuracy, but in general they match. The same with temperature. So this is 10,385, and this is 1 times to the 4, so it's 10,385. And then you have the same for the electron density, the same for the velocity, and the same for microturbulence. Okay, so then the important thing that I want to really show you here is that what we are doing now is to confirm that test is equal to what we have in the Atmos file. In day 8 was after running write 1D Atmos, we were checking that the Atmos file was what we wanted to have. Okay, so then just check the other 6 values. So we go down a bit, and this is the hydrogen population. And then what we have is, this is 3 to the 8. So you can see that there's also 3 to the 8. Then this is 157, that this is 1 times to the 2, 10 times to the 2. Sorry. Yeah, you can understand. And then 2.7. So here is 2.7. Then 0.8, here is also 8, 10 up to the -1, and then 3, sorry, also 0.5, and then here is also 0.5 because this is -1, and then 3.6 times 10 up to 9, that is also here. Okay, so then what we are doing is checking that the first value for test in position 60, 150 is exactly the same value that we generate when we use write 1D Atmos in the folder day 8. Okay, so then until this point, it seems that it's okay, it's correct. So then let's do a second verification. That is, one is going to be related to the magnetic field. So as I said, I also saved the magnetic field here, but I think I haven't showed you how to read, at least with IDL, the magnetic field that you have created in XDR format. So this is how you read it, because I think I didn't do it, and it's not straightforward. So you need to use this instruction. Then inside you define the arrays where you want to save things, and then you also need to know the dimension of the arrays you want to read. So then we just read field strength, inclination, and azimuth. And then what I'm printing here is the first value of these magnetic field parameters that we have read from the day 8 computation. And then we compare that with the values of the array that we create in this script, that is test, for the pixel x60, y150, and then index 5, index 6, and index 7. And then 0 is the first height, that is the top of the atmosphere. And then if you run this again, you will see that they are exactly the same. So what this means is that after all the transformation that we did, that is different from the one in day 8, what we are getting is exactly the same RH needs and RH will read from the Atmos file and the B file. So until this point, I think everything is consistent and correct. Okay, so then we make the file we need and we test it that is consistent. So now we have finished the first part. The important thing here is that this is from the previous class, I think, but this is a bit different. So I just want to show you that this may be a bit confusing. First, I think the idea is that we are covering how to do things with IDL that are probably 20 years old because it's how things started. Then you're probably now using Python scripts that handmade, and I think these are like 3 months old, so they are very, very new. And then we are combining this with the Python wrap that is like 2 years, 3 years old, and it was also created by different people. So it's okay if you see that things are not completely connected, but it's because it's time differences and also creator differences. But the important thing is that if you double check things, it should be consistent. And this is what we did in the first part. Okay, so until this point, I think we have the input ready. Okay, so then is there any question before I move to the parallel wrap? No? Okay, so then we have a different folder that I call it parallel RH online course. And here we have everything that we need for running the parallel wrap. In day 14, we have one zip file that is this one. And this one is from Ricardo. So it's the same elements that you have here with an example atmosphere to run it. It's very small. So then you can use this as a reference package, but also I will provide this one. And this one is the atmosphere that the configuration that we are going to use today. That I changed a lot of things compared to the reference case from Ricardo. Okay. So then what do you need for running the code in parallel? So you need basically 3 things. You need the initialization.input file, like we are going to cover it now. And you need the parallel master, that is the Python wrap that really handles everything. And then you need the folder called run files. And there is where you put the RH files, the keyword.input, the curux.input file, the atoms file. So everything, anything that you need that is not located in the RH reference folder, default folders should be there. Okay. Then you have this that is as a reference for you, maybe for how to install it or what package you need. I think this install.py, I think this is new, so I don't know exactly what it is, but I guess if you run it, maybe it will install all the packets that you need, but I haven't tried. I usually just go by hand, or sometimes the computers I use, they have the default, as default, they have a lot of Python modules. So give it a try, just to install everything that it should be needed. And if you have crashes or something is not working, I think you just contact Ricardo and check if some library is missing, or maybe the version of your library is not the one that he's using. So just that. But essentially what you need is the input file, the Python wrap, and then run files. Okay. So then let's go to this file. I'm going to close this one just to keep things as simple as possible. So this is the configuration file, and it's very simple, only 10 lines. Okay. So before getting to each line, Ricardo has been working, because initially we had different Python wraps for everything, for SER, for Modelador, for RH, for design. And Ricardo has been trying to make just a master Python wrap, and then internally just through labels to just work as for design, work as for SER, or work as for RH. So then you have here SER, design, Modelador, and RH. And then in front of each, or after each number, you have a capital letter that tells you that this instruction is used in different versions, on different codes. So in this case, this instruction would be used by SER, design, Modelador, and RH. And this is because it's the number of cores. So you always have to define how many cores you want to distribute your computation to. So then you can run the code. Okay. So then, very, very simple. You need to provide the number of cores you want to use. Then where your atmosphere is. So then in this case, I'm using, so you remember, we were inside RH just for simplicity, and then we were in this folder and we create this feeds file. Okay, if I go back just 1 second, you can see that this is the name that we have here. Okay, so then also you need to provide the coordinates that we want to run your computation over. So then 1 is if you use your full map, but then you can provide x0 or initial x and final x, and then initial y and final y. Okay, so in our case, if you remember, we were testing the initial pixel that was 60 and 150. So then our x0 is 60, our y0 is 150. And then if you remember, the size of the small field of view that we used was 230 pixels. So then 60 plus 230 is 290. And then 150 plus 230 is 380. Okay. Then we have this debug mode that, if you remember, if you put 1 and you run the code over a few pixels, it will save the region, so the folders containing all the information that will be passed to the code. It will be saved in the result file folder. So then you can check that what you are trying to provide, design, RH, or serve, is exactly what the code is doing, because maybe there's an issue and it's reading a file from somewhere else, and you want to change that. I tested and it's not working in RH, and I talked to Ricardo, and he probably will implement it. So for now, just leave it in 0, but I will check with him, and then I will ask him to upload a new version with the possibility of just running for 2 or 3 pixels this mode, so then you can check what files is RH using. Okay, and then we get to the easiest thing, because if you see, this is only for share and desire, this is only for share and desire, this is for share and desire, so we will cover it again with desire. This is also share, desire, and modelador, so it's not related to RH. And then here again, we are in RH, and this is where your code is located. So in my case, again, this is RH 2021, RHF1D, just write it this way. And then the Python wrap will go to that folder and will execute the RH executable that is there. And it will also create temporary folders there that contain the information of each pixel, and then they will be eliminated. So if you go to this folder when the code is running, you will see folders. They are called, I think it's PRH- some number. Okay, but they will be temporary, just until the code finishes, and then it will be clean. Okay, then this is only for RH. You need to specify the depth scale type, and this is because RH needs to know what type of scale you need, and remember, it was written, you can check it. It was written here. So then it's just to keep RH informed of what type of scale we're using. And then here you can provide that if it's mass column, if it's log tau, you provide T, and if it's geometrical height, like in our case, you provide H. Okay. And then this is applicable to all the versions, or I mean, all the codes, but I think it's going to be obsolete, because we don't want to send mails to Ricardo or to someone else when the code is finished. So probably this will disappear, but it's an instruction that if you want to receive a mail when the code is finished, you may ask. But I don't know if it's working. I never tried, but I don't know if we will be continuing to further versions, because yeah, I don't know if it's very, very useful. Okay, so then we know that we have to run the code and we have prepared everything. Here, just basically what atmosphere we need, the number of cores, the coordinates over the map that we are providing, and then where RH is located. Okay, so with that, then, oh yeah, that, yes, go ahead.
Carlos, yes, what is number 5? Is it something important?
Not for our case. So this is basically for design. In fact, I
Oh,
think
that's for desire. Okay.
Yes. I think this is for inversions, but we will cover this in the design course next year. But I think this is, just let me check. Yes, this is how the initial atmosphere that you want to use for the inversion. So sometimes you can have a set of atmospheres. Sometimes you want to do some clustering neural network studies. So in this case, it's only for inversions and with zero desire.
Okay, thank you.
Okay, yeah. So then, thanks for the question. But I think no more questions, right? No. Okay. So then, if now we go to run files, and there you will see that there are two folders. In the case of Atmos, we forget about it because it's related to SER and design, so we don't need to do anything with that folder. And then we have the keyboard.input that if you load it, it looks a bit different to what we are used to. And this is because Ricardo reads the keyboard.input that you provide, and everything that is commented is removed. He explained me that it's better for him to handle everything and transfer information. So what you have to do is you take the keyboard.input that you want to use, you put it there, and then after running the code, everything that is commented will disappear. So if you want to add something that was commented, please always keep a copy of the keyboard.input somewhere, because everything that is not used will disappear. But in principle, I think I configured this file exactly in the same way as the one we used in day 9. The only thing that is important to bear in mind is that I'm now putting the threads to 1 because we are now running in parallel. And I think it's not correct to run the code in parallel and at the same time ask the code to use multiple cores for the wavelength computation. So this parallel version was for dividing the wavelength points in different cores. So this is what we use in the serial version. But in this case, we are dividing the atmosphere in different cores. So we don't want to divide again that in different cores for the wavelength, because I think we can have communication problems. So always try to keep 1 here, and then you can add much more points in this number of cores. Okay, but I think the rest should be, just please double check it, but it should be the same that we had in day 9. Okay, so then we go to inputs files, and here again, so we have the atmos.input that is the same that we use. So remember that we had active. In this case, I'm saying the calcium atom is in this local folder, so it's this one that you see here. And I'm saying that the rest of the atoms that are used for passive computation, they are located in the default folder of the RH code. So it will be in RH 2021, okay? But this one, that is the one that we modified explicitly for this course, is located here. So I don't want to mix it with other things. And then you can see that is the atom that we used. Remember that we had more points, then it was asymmetric, and then we also changed these Q core and Q wing values. So this is, if I'm correct, I just copy the atoms from the day 9 folder, and it should be the same. And then we have the Kurux file, the Kurux configuration file that will point to this one, the molecules, the gray for the projection, and then the wavelength grid. Okay, so this should be the same. No changes here. Okay, so then with that, we are ready. So what I did was configure this part and then copy in this folder all the files that we had from day 9. Okay, so then with that, just for simplicity, let's compute. So for example, from 60 to 70 and from 150 to 160. So this is 10 by 10. So then we are here. So then we just write Python. In my case, I do it this way, Python 3. And then you just to this, and then it will read automatically this one. And then if you type enter, then you will receive some message, and then it will set running the computation, and you will see a message like this, and it will finish. So we did 100 pixels in 6 seconds. The full 230 times 230 pixels with this configuration, I think is 30 minutes, 20 minutes. So we are really saving a lot, because before it was like 2 days, and now we are just under 1 hour, definitely. So it's really, really good to have the option of making it parallel and scaling with servers that nowadays you have easily 50 cores, but sometimes even 100, in my case, 128. So it's relatively easy to have a lot of cores available these days. Okay, so then when you run the code like this, it finishes. And then what it did was, in results, it created this file, okay, that is a fits file. And also it created the folder errors. In this case, it's empty. But if you have that something didn't work, then you will probably have an error here. So then you can go there and check if your configuration was not correct or something is missing. Okay. So then I did, just let me go back here and then put the original field of view. So I ran it for this field of view, and then the results are saved in run 4. Okay, just let me remove this. So then here, I have the RH results, as I said, the error folder, just to be sure if there's some issue. Then I put it in configuration files, and this is because I run a lot of things and I want to be sure which keyword.input I use, which initialization.input I use. So every time I run something that I know I want to keep, I just create a folder here, and then I just copy everything. The initialization.input, the Python version, and the input files. So this, I put everything there, and also the output. And the idea is that you see that this says run 4, and this is because this week we had issues. So I had to run it 4 times to reach a good solution after debugging a bit with Ricardo. So I think you could have more bugs. So if you have anything, please report to us, because I know that sometimes things we upgrade them, but sometimes some bug appear or is left. So if you have issues, just contact us. Don't think that you are doing something wrong. Maybe it's just that there's a bug and we can solve it quickly. Okay, so then run 4, these are the results. And then what I'm going to do is to read the results and make some plots similar to the ones we did in day 9, just to compare and check that everything looks the same. Okay, so then this, just let me close this one. So then this read.pro is the script that you have there. And then we are reading the full 4 stocks array with this instruction. And then the wavelength information is also encoded in this extension instruction, like in the case of bifrost. If you remember, geometrical height was included as an extension in all the atmospheric parameters. Now the wavelength is the same. So in order to read, just put the name of the output file and then this instruction, and then you have it. Okay, so then the first thing we are going to do is just plot the continuum intensity at 500 nanometers. If you remember, in this case, we haven't said anything about the wavelength. So the file, the output file has everything. In day 9, you remember, we cut it, the wavelength of interest, because we were not interested in calcium HNK or some blue or ultraviolet wavelength. But in this case, we have not provided any information. So the code, the Python wrap, will always provide the full wavelength vector that RH will compute. Okay. So then we looked for 500, that it corresponds to this index. And then we are going to study or to plot the continuum intensity at 500. So I'm going to just reform this array that is X, Y, wavelength, and a Stokes vector. So it will be 230, 230, then the number of wavelength points that we don't know now, and then 4, the 4 Stokes parameter. Okay, but we want to compare what we have in day 9. So we are going to use these coordinates later. Okay, this is just for the plot, just for the axis, because we want to know if from the full field of view where we started. Okay, so we plot the continuing intensity at 500 nanometers, and this is just for the labels. So this initial x and final x is just for the labels, and it's multiplied by the pixel size, so it will be megameters, and then we just plot everything. So then let's check how this looks with this one. Okay. Okay, so it looks good. We have the granulation, we have the magnetic patch, and this is what I was saying. So this is referred to the origin of the full bifrost snapshot, so we know exactly where we are. And then we have some small dots, so 1, 2, 3, 4, 5. I think we didn't have them when we did the serial run. So I want to sit down with Ricardo and Han just to check what could be the difference. Maybe it's something in the configuration and I made a mistake, but in general it's just 5 points and the rest it looks okay. So then what we are going to do in this case is just remove them and replace them by the neighbor one. So just for this case, I'm just looking where the intensity is lower or equal than 0. And then I just replace that by the closest value. So then we are going to do the same plot and we call it clean. And just we check. And it looks much better. So then it's just 5 points and we can remove them. So then this is the first thing we are going to do. Now for the full Stokes vector, we are going to go to those points where something happened. I don't know who, yeah, there's a chat. Yeah, I think Ryan, you can tell us. Okay. Well, I will read it. You said, I tried to synthesize iron 6302 in non-LT from this bifrost simulation a long time ago, and there was always a very small number of profiles that didn't converge. Could never figure out why. Yes, I don't know. I think in that case, I need to sit down and check if we increase the number of iterations or something else. But my impression is that in general, if it's something like from 200 times 200 pixels, 5 or 10 are out, you can just clean them because it's less than 0.1%. But we can study what happens for those pixels. Okay, so then what I said is just let's remove. Let me see where we are. Yeah, we did the plot, and then let's continue with the continuing intensity at 850 nanometers. And then the first thing we're going to do is that for making the plot similar to, or the program similar to date 9, we are going to choose the same wavelength range. So this is from day 9, okay? So when we cut the wavelength range, the initial point was this value, and the final point of the wavelength vector that we choose was this one. So now I looked where in this computation those values are, and it's just this value and this value. So the wavelength range is the same, and we can see that this is exactly the same as this one. So we are just going to reformat everything for just repeat exactly the same plot. So we are going to separate the array in I, Q, U, and V. And then we are going to select the wavelength range that we use in day 9, and then the full domain. Okay, and also the same for the wavelength. So it's just repeating exactly the same we did in day 9, although we are now using the parallel route. Okay, so then we are going to run a loop, and then I'm going to tell the code, please let me know if the continuing intensity at 850 nanometers is less equal than 0. And if this happens, just replace that pixel for the closest one, And then with this, we clean this 4 Stokes parameter. Okay, so now let's check what happens at 850 nanometers after cleaning those wrong pixels. Okay, so now it looks good. And then the next step is to check if now it looks nice, but it's in SI units. So I want to know if this is consistent with what we usually have with continuum, normalized continuum intensity levels. So then what we are going to do now is just simply we compute the average intensity for the continuum value. So this is 850 nanometers continuum, and we normalize the 4 Stokes parameters by that value. Okay, and now we make the plot again. And in this case, I'm providing the threshold. So it should go from 0.6 to 1.5 of the intensity normalized to the continuum intensity. Okay, so then this B looks like this. Okay, so then now we see that the spatial distribution of the intensity signals are reasonable, granules, intergranules, bright points in the magnetic field location, but also the values are reasonable. So the average intensity goes from 0.6 or something like that to 1.4, 1.5. That is for the simulation, it's okay, it's correct. Okay, so then the last step is, and what about the polarization signals? So then what we did also let's check about the intensity signals in different positions along the line, and then we will go to the polarization signals. So what we did in day 9 was to pick the line core wavelength on rest, the rest wavelength, and then one reference wavelength in the wing. And now we are going to plot the continuum at the 150 nanometers, the blue wing, and then the line core intensity. Okay, so these are wavelength index. And this is calcium 2 line. Okay, so it's this one. Let me open this one. It looks a bit small, so let's make it bigger. So just, I think you can see it now. So granulation, again, is the same, so it looks fine. Then we have in the wing the reverse granulation pattern. So now granules are darker and intergranules are brighter, but it looks smooth and nice. And then we also have the line core intensity that, as we said in day 9, it's complex. We have like some kind of threads. So this looks like calcium to line core. Okay. So then again, it looks consistent. We don't have issues. I don't see wrong pixels, at least at this level. So I think it's working okay. And then, as I said, the last test is to compute very simple indicators from the polarization signals. That will be the maximum Q, U, and V signals, and just check that they are not 100% or 200% of the continuum intensity, or they are not 1 × 10⁻⁵ of the continuum intensity, because if not, then it means that maybe when we did the transformation of the magnetic field, we did something wrong. And maybe instead of providing it in Tesla, we provided it in Gauss, or we provided it in a wrong way. Okay, so then very simple test. We just compute from the absolute value, because if you remember Q, U, and V, they can be either positive or negative. So I just want to know what is the maximum amplitude. I don't care about the sign. So from the absolute value, I compute the maximum for all the wavelength range that is defined by these two index, that is essentially the line core of calcium line. Okay, you can make a plot of the line using wave of 100 and wave of 160, and you will see that is the central part of the line. Okay, so with this, we do this plot, and it's this one. And you see that in principle, it looks fine. So we have that the magnetic patch was around here. So we have that the concentration, it was a network patch. So it has mainly longitudinal magnetic field that we saturate at 10%, and it looks reasonable. So we only have signals here and here, but not outside there. And then you see that outside this patch around here, you have linear polarization, and this is probably that the magnetic field lines are bending as we move with height. So the central part that is more vertical is this one, and then as it bends a bit, the inclination, so this inclined magnetic field produces linear polarization, and is the one that we are seeing here. And the amplitude around 5 × 10⁻³ or 0.5% is reasonable for the calcium light. Okay. So then I put in day 14 in HD figures, I put calcium pole, that is the one that we checked now. And I also put it day 9, that is the one from the previous class. Okay, so from day 9. Just let me move this. So it's just by eye, because I wanted to allow you to double check this if you are interested, but I think it's essentially the same. If there are minor difference, could be because the keyword or input, maybe I didn't use the correct or the same keyword, or maybe something was lost, but my impression is that they are the same, and the same for Q and U and V. They look the same to me. So I think it's almost the same. So unless I made a mistake somewhere. Okay. So then with this, I think we finish. And essentially what we have done is we run the code and we just read the output here. We clean it from pixels that didn't look okay. And then we just repeat the same plots without changing anything from day 9, just to compare that everything looks consistent. Okay. So I think that's all for now. So before going to the presentation, any question about something related to this part? No? Okay, so then as always, if you have any issue installing the code or trying to run the same sample, just contact me or contact Ricardo, and we will try to solve it. Okay, so then for now, let's go back to the presentation. We put this.
Carlos, just a quick question.
Yes.
How fast is this compared to serial run? You said 20 minutes, but is it like 20 hours? Sorry, 2 hours run in serial?
No, 2 days. 2 days.
2 days, yes.
Yes.
Oh, okay,
yes,
okay.
Yes.
Bye.
Yes. Bye, Han. Sorry, yeah, Han has to leave.
Yeah, sorry.
Bye. Thank you. Yeah, but I think it scales. So when you run it in serial, you can provide some kind of parallelization through the value. If you remember, just let me go back. In the keyword.input run files. So here you can provide some kind of parallelization. So you are telling array, please use more cores for computing other wavelength points. So these speed up things a bit, but compared to just distributing atmospheres between pixels, it's not, it's much slower. So in my case, I think around 1.5 days or 2 days in serial mode, the same computation with the same computer, and using the 100 threads that I set in the configuration file, is around 30 minutes. So you can essentially scale by the number of cores, almost is directly. So if you have one node for serial and it takes 10 minutes, if you use 10 cores, it will be 1 minute. Almost a linear correlation.
I see. Yeah.
So it's much faster. Yes.
It's much faster. Yeah,
it's much faster. Yes, and this is a normal server. We are not getting into supercomputer or cluster. This is just a normal server that I use. It's a Linux machine with a normal processor. It has a lot of cores, but it's just a normal one. So if you can get to super computer like 500, 1000 nodes, then you can really do computations really fast. Although I think 30 minutes is what you need to read the mail. so I think it's okay.
But Carlos,
yes.
If I can say some word about that,
yes,
I think it's going to scale with the number of cores. There is no almost improvement in the performance of the technology of the core. That is at least my experience. When I use the servers at Lockheed, for 1 pixel, it takes me 1 hour, and I go to play at this,
Yes.
which is a NASA supercomputer, it's going to take 1 hour for 1 pixel.
Yes.
The difference is that in Pleiades I can run in 2000 and in Lockheed maybe 700. But
yes. Yes.
yeah,
Yes.
yeah,
Yes. Yeah. This is maybe I say it incorrectly, but this is what I meant. So I meant that here I have 100 more or less, but if you go to a cluster that has 500 or 1000, it will be 10 times faster. For example, in the case of 1000. But in principle, I guess the cores usually they are a combination of the cores that are similar to the ones we use, so they should not be faster in terms of per core performance, but it's just that, as you said, you have up to 2000, but this is a lot. You don't have time to read the mail with 2000.
Yeah.
Okay, so then any additional question? No. Okay, so then I will go back. So as always, homework is try to run the examples I prepared. So in this case, it's to run the script ideal Bifrost transform parallel, I think is the script, just to check the prints that I put and check that everything is consistent. And then try to install the Python wrap. So for example, in my experience, this server is new, but they load a lot of Python routines, so I didn't need to install almost anything. But maybe in your institution things are different, so just try to check that you have all the Python libraries, and if you just run it and it crashes complaining that some library doesn't exist or something like that, then just go to Ricardo, that he's the expert on that, and probably it will be fixed in no time. Okay, and then when everything is working, try to run, let's see, as a chat. Yes. Okay, so Ryan is saying that in his case, he had weird bugs with Python dependency, so it's worth updating them in addition to checking that they are there. Yes, yes. And it's also important that sometimes if you are the root, then everything is smooth because you can change things. But if you are not the root, then things become a bit more delicate because you have to ask permission and you have to justify what you're changing. So just try it, and if not, we will help. Okay, so then what I was saying is, if everything works, you can run it, then try to run the example that I ran today, check how fast it is, check that you understand how things work, and check that when you run the read.pro script inside the result folder, you get the same figures that I get. Okay, so I think that's all for homework. So then next class. My impression is that we have been thoroughly covering RH, and I think at least in 1D we have done most of the things that you would like to do, at least in normal situations. So my impression is that we can conclude this course, and I hope you have learned a lot. But I think RH is a bit more complex than SER, so I guess that you may like to learn new things in the future. So I think it's fine to have it as a living thing. So if at some point, I don't know, maybe March or April next year, you said, I was trying to do this and it didn't work, we can make a new class just for that. And it doesn't need to be just correlated with this course. We can have additional classes in the future. I think we can have this online session as a living thing that we add things on top, and as they're going to be in YouTube and also the files will be in Dropbox. So if you have some things that we didn't cover today or in the course and you want to still cover in the future, just let's start discussing them, and we will find the time for me, maybe if it's new, for testing things, and then we will find a place for giving an additional tutorial, and then everyone can also learn how to do it. So if we finish RH, then we are ready for going to design, finally. So it's been, I think, almost 1 year. So, so I think it's been a bit long. But as I said, and I think you will agree with that, I think now you are much more ready for understanding not only how to run design, but also to know what is doing internally and how to do things with RH, but also how inversion codes work, or how non-LTE synthesis is done, why you need an atom, why things are done this way and this way. So I hope it's a journey that you have been enjoying, and also I hope people will enjoy in the future as well when they try to learn design. But then it means that yes, we finally are going to start with design. I think Basilio is also excited about that. So then it means that next year we will start with design. I need some time because it's Christmas time, but also I need some time for preparing things and to also work a bit on other projects that I need to dedicate some time. So I think Friday 28th in January will be the first class. And I think it will be like now. So every 1 week or every 2 weeks, depending on my availability, we will cover design, 1D, serial mode, then we will cover response functions and everything, then parallel wrap, and then you will be ready, hopefully, for analyzing your data, SST data, DKIS data, hopefully, or other type of data. So I think we are in a good pace, and I hope you will be ready for design. So before wishing you nice weekend, do you want to ask something else before closing the telecom?
Indeed, yes, I want.
Okay. Okay.
So now that Ryan mentioned that he's inverting NLT, I just remember a question I have had for a couple of weeks. I think we mentioned this before, but I forgot the answer. Imagine that you are inverting or synthesizing two lines simultaneously in non-LTE.
Mm-hmm.
In addition with other lines that you consider for the opacities and all these things.
Mm-hmm.
In the atoms.input file, you consider you have to put both lines active NLTE.
Yes. Yes. So
okay.
so if you go here, input files. So this is the atoms.input.
Yep.
So
yep.
So if you are, for example, calcium H&K and calcium 8542,
yes,
they are reproduced by the same atom. So you just need to put this atom as an active.
Yeah, that's
okay.
clear.
But imagine that you want to have sodium D1, D2.
Yep.
So then if this atom reproduces those lines, that in this case is yes, then you have to put it here active.
Okay.
And then perfect. you have to go to the atom. What I will do is copy the atom to the local folder here, and then change it to just provide a good number of reference points to be sure that it's asymmetric, the computation and everything. And then this atom will be the one providing the information regarding sodium D1, D2, for example. And then this atom will be the one providing information relating to calcium.
Carlos, you locate these files in your current directory just for safety reasons, right? It doesn't matter if it is.
Yes,
okay,
it's for safety reason, and because sometimes you change things and sometimes even test. So imagine that you said, oh, I want to synthesize sodium D1 with 1000 points. And then you are doing the test and then you're happy. But imagine that it's in your default folder and you forget about that. So then you are running these different computations and you are always using 1000 points for sodium that is making your computation really, really slow. And this is just one example. But other example could be that you change something and you put PRD or you put CRD or you change things. So in my case, I always want to have the default atom without touching it. And then I will bring a copy of that. I put it in the local folder. And I know that only that folder is the one that changes things.
Yeah, okay. It's a good idea. Thank you. Thank you, Carlos.
Yes. An important thing, Alberto, is that you can, so any non-LT line that you want to add from a different atom, you have to put it in inactive. So for example, in this case, imagine that what we said, but you also want to have H alpha. So you put here active, And as I recommended, you just put it in your folder and that should work. But sometimes, for example, these neutral, so silicon, oxygen, carbon atom, sometimes they don't have the transition. It's not defined. So then in those cases, you have to look for a special atom, or if someone has created the atom that contains the transition of it.
Yeah. Thank you very much. It's very clear, and I just want to double check that it was. Thank you, Carlos.
Yes, and we will do this with desire. So for example, with desire, we will do test where we embed calcium, synthetic calcium, synthetic sodium, synthetic potassium. This we did for the paper, and I will show you in the class. And there you will see that we need to have each atom. So for example, in this case, it will be this one also. This atom will be active, and they will provide those lines in non-LT. Okay. Okay, so then just let me go back. Okay. Okay, so then no more questions.
Perfect. Thank you.
Okay,
Carlos.
thank you, Alberto. Okay, so then we were here, and I just want to wish you Merry Christmas and a Happy New Year. So, and I hope to see you next year as well. Okay, thanks a lot, everyone.
Happy New Year.
Thank
everybody.
you. Happy New Year.
Be safe.
Yes, take care.
Thank you.
Bye, everybody. Take care.
Bye. See you.
Bye-bye.
Bye.